This module, we talk about the SRE architectural considerations and how they appear, how they shape and form, how they evolve from traditional architectures to cloud native architectures, and where they are proceeding in today's world. Now, SRE architecture considerations involve designing software systems with three things in mind. That's reliability, scalability, and operability in mind. Now, what do I mean by this? Reliability means my system is reliable to operate at 99.99 some percentage, which means for this much percentage of time, I can be rest assured that my system will operate reliably, it will be available. Scalability means that my system will be able to scale up to demands as the load increases, maybe on certain events like a Christmas day, a Boxer's Day, a sale event happening, my system will be able to scale up. And at the same time, my system will be able to scale down when the resource hit, the population hit on that system is not so much. When I know that there is a lull period, my system will automatically scale down to be able to save on money, efficiency, resources. Operability means my system will always be in an operatable state. My system might be reliable, meaning it is up, but some parts of the functionality might not be working and they might impact operability. So all of this put together are the architectural considerations for an SRE. Now let's dive a little deeper into some more dimensions. To achieve this, SRE teams need to partner on the architectural design. Why? Because as the architecture gets finalized and as it gets evolved, the SRE team need to get their inputs in to be able to tell them if there are issues on scalability, designing it, on how the pods are getting structured, on how they are getting scaled up in a cloud native environment or even an on-premise environment, on what workloads should you deploy these kind of applications. So an SRE input is required on the architectural design, and we'll talk a little more detail on this as we go along. And the SRE team also defines pattern for software structure, which means they have an say with the DevOps team on how software is built and how it is structured for reliability, meaning how much resources should be allocated, how it could be scaled up, should there be caching or not, if yes, how many layers of caching, is there DNS availability, how do you ensure that? And then it gets more complicated as you move into the container world and the serverless world, but things like that. And third is the automation for efficiency, because one of the goals of the SRE is to automate away all the toil heavy processes, which means anything manual, anything repeatable got to be automated. What happens as a result of doing that is you free up time for innovation and you ensure more efficient workflows. And then there is observability, which is to make informed decisions about whether you need to change something in the workflow or in the architecture. And that decision is coming from metrics which you have collected across the deployment lifecycle. And then error handling as resilience, because you design strategies to detect and recover from failures, making sure that your system continues to be reliable and responsive even when there are issues underneath it. And all of this has to be done by managing the error budgets to be able to ensure that you can manage and prioritize incidents and ensure that the system operates within the agreed upon reliability budget. What's a reliability budget? I'm sure we've already covered that, but each portion of the reliability budget has to be well spent and well focused on. So these are some of the architectural considerations for an SRE. Now let's look at the importance of SRE and data pipelines in modern software development. Now, number one is to ensure data quality and consistency, because everything further down, all decisions are built on the quality and the consistency of data that goes into these data pipelines. Now, how is that done? By data validation, cleansing, and transformation steps. And as we go deeper into data pipelines, we'll talk about the types of pipelines, the ETLs, the bigger forms. We'll get into the weeds of it. But this is just to give you an overview and tell you that step one is to ensure that the right data is getting in the pipeline. Then step two is to ensure that data-driven decisions are enabled by collecting that large volume of data, by analyzing it, by processing it, and by creating some patterns. And how do you do those patterns? By supporting AI and ML, right? Because when you start doing that, then you start training your system on historical data with the ability to spot patterns and then relay back those patterns so that you can make decisions. And then you facilitate that by real-time analytics. And those are very important in things like fraud detection, recommendation systems, operational monitoring, where you need real-time data plugged in into the historical patterns to be able to take certain decisions. So a data pipeline architecture is a collection of items that captures, processes, and transmits data to the appropriate system in order to get important insights. So capturing data, processing data, and transmitting data in order to get insights. And we have seen the stepwise in the previous slide as well. Now let's dig a little deeper into this. A data pipeline is a broader phase than ETL pipeline, where ETL essentially talks about obtaining data from a source, that extract, change it, which is transform, and then loading it or feeding it, that's the L part, loading it into a destination system. So an ETL is extract, transform, and load. A data pipeline is a bigger set, out of which an ETL is a subset. So let's dig a little deeper about this. What's a data pipeline versus what's ETL? So a data pipeline transfers data from one system to another. Typically, there is no data modification or loading. It can be continuous, real-time, or hybrid, and it's better suited for real-time applications. ETL, transforming and loading of data into a data warehouse. It's mostly batched based. That's how we have seen ETLs work on large systems, on legacy systems as well. There is a time set up for batch manipulation of data. And it's typically for data migration, in-depth analysis, things like analytics, BI, those kind of things. So those are the fundamental differences between a data pipeline and an ETL. For the sake of this session, we will focus more on the data pipelines, because that's where the industry is moving into, that's where the AI ML algorithms are coming in, that's where the focus is these days. Now let's look at typical data pipeline architecture. Now this is a broad-based architecture. I've taken it from an article from DZone, but I thought that this architecture, this picture specifically, captures all the facets of a typical data pipeline architecture. Now there are obviously nuances in each one which are not highlighted here. This is just to give you an overview of what's happening here. So number one, data sources. It could be a database, it could be flat files, it could be SaaS applications, it could be streaming data coming in from your IoT devices. So different forms and shapes from which your data sources align. And then that data is ingested and it could be ingested using a batch data processing or a stream data processing. And then that, upon that, that is ETL or ELT. So ETL is, we spoke about that, extraction, transform and load. ELT is extract, load and transform. And once that is done, then that goes into a data storage, which could be a data warehouse, it could be a data lake. And from that, there are different types of visualizations, business intelligence, AI/ML, which is the data users on how to make sense of this data, how to create patterns, how to visualize this. All of that is happening. That's the user side of it. And then underlying all of this is data governance. So is my data safe? Is my data abstracted? Is sensitive data protected? All of that is data governance, orchestration of all of these pieces, and obviously monitoring of each of these individual pieces to make sure they all function properly. Now let's look at some toolings in here. I'm just giving some high level toolings. There are obviously a lot more in there. So processing is Apache Spark or Hadoop. Data streaming is Flink or Kafka. Data storage is Redshift. It could be Snowflake. It could be Google's BigQuery. Data lakes could be again Apache Hadoop. Some people use S3, Amazon's S3 for data lakes as well, or it could be the Google Cloud Storage. Those are also used as data lakes other than the specific proprietary solutions. In the governance orchestration, you have the orchestrators like an Apache Airflow, NiFi. There are several others as well. And in the monitoring, we all know of ELK, Elasticsearch, Logstash, Kibana, this Grafana, and there's Splunk and several others in this area. Right, now let's look at data pipeline architecture designs. So first, extract, transform, load. ETL, we spoke about that. It's a scalable and flexible with cloud-based ETL tools and services. This is offered out of the box by a lot of organizations, and it gives you a real-time or a near real-time processing for faster insights and decision making. So that's the older forms, ETL and ELT, which is cloud enable native complex transformations within the warehouse. And it could have solutions like Snowflake's, Google's BigQuery, and etc. There are several other solutions. So these are the two old ones. Now let's move to other things. There are streaming architectures which could handle large data volumes, support sophisticated processing. So for example, there is a football match going on, there's a soccer tournament, there's a cricket tournament, huge volumes of streaming data and millions of people vying for that. How do you handle that? So it integrates your stream processing frameworks and cloud services for scalability and for fault tolerance as well. Then there is the exact opposite of it, which is zero ETL, which supports efficient data lake storage and processing frameworks, and it integrates with tools for schema on read and late binding with flexible data exploration and analytics. And then there is data sharing, which supports your data exchange through multiple distributed environments. And of course, it integrates with your encryption, authentication, access control for security, compliance, and all of that. More important here, because you're talking data sharing. Of course, security is embedded in each of these layers, even if you are at the ETL and the ELT layer as well. Now, how to choose a data pipeline architecture? We'll give you some examples on how SREs should be aware to choose a data pipeline architecture. It depends on the data processing needs. What's the volume of data? Is it large scale or is it real-time streaming data? What's the type of load? What's the type of data? Is it structured data, semi-structured data, unstructured data? What's the type of data processing? Is it real-time or batch? What's the accuracy and the reliability of the data? Are there any integrity concerns which need to be resolved? So the data needs to be massaged, it needs to be brought into a typical format, not the structuring data, but some massaging of the data before you start processing it. So this is around the data processing. Then what are the use cases? What's the type of analysis that you want to do on that data? Is it simple aggregators? Is it very complex transformations? Or is it predictive analytics? What's the acceptable latency? Do you need real time or will you tolerate some delays with near real time? What integrations with other systems or apps do you need? Do you need to integrate with specific cloud services, databases, analytics platforms, and so on and so forth? What scalability are you looking at? And how do you handle the ability to grow the scaling data? Does it suddenly scale into millions and hundreds of millions of users for 2 weeks when there is a particular sporting tournament happening? Is it that high of a scale, or is it just an incremental scalability? What are your requirements to scale horizontally and to scale vertically? And when you're scaling, what are your reliability and fault tolerance mechanisms? What's the permitted limit in each one? And then above all of these technology is the skill set and resources. What roles do you need? What experience level do you need? What skill set should they have? Is it cloud native? Are you dealing with some proprietary data for which skill sets are not available very commonly? Right? Have you done a lot of customizations on top of traditional cloud native stuff for which people will take a lot of time to upskill themselves? And then how future proof do you want your solution to be? Because it has to be compatible with your existing setup, but your existing setup might change into cloud native. So how willing are you to be okay with a vendor lock or a technology specific lock? Right? So those are some of the considerations for a data pipeline architecture. Okay, now let's look at the state of data engineering report. This is by the guys at Lake FS, and it's a beautiful picture which organizes all the tools in that area by certain categories. So you have an ingest, you have all the data lakes, you have data version control, things doing metadata, you have the compute engines with distributed compute, analytic engines, you have pipelines within that, the orchestration tools, you have data observability tools. Then in your practitioner app, you have the ML ops end to end, and then you have the data centric, the observability and monitoring, vector databases, what kind of notebooks people are using, like the Jupyters of the world, then the analytical workbooks, and within governance, you have data governance, data cataloging. So it's a brilliant collection of all the stuff that is out there. Now, they also, along with this report, they also publish some inferences. So, some trends. So, first is obviously not surprising, the Gen AI influence, which is that Gen AI, generative AI, is influencing on storage, compute engines, ML ops, observability, almost across every category. And this is not surprising, we know about this. Trend number 2 is expansion of product offerings, which means that beyond AI, the market is generally struggling and companies are expanding their products to adjacent domains to increase revenue. Which means if somebody is in pipelines, they are now going into the adjacency areas so that with minimal change in their product, they can enter into a new category. And then trend number 3, which I found most interesting, is the open table formats and their catalogs creating closed gardens. We are all familiar with the Databricks versus Snowflake, stuff that is going on around there. But those kind of things are fueling innovation, niche players are coming in, and because of this, the data engineer is a winner. Now let's talk about machine learning pipeline architectures. Now when we talk about ML, straight away we are thinking maybe a Jupyter notebook, and that's where an ML practitioner starts off. by creating something in his Jupyter notebook locally, deploying it locally, setting it up locally. That's all fine, that's all great. But when it comes time for productionizing stuff, you need to think about a workflow. And that workflow takes your data from its raw form, performs operations, generates predictions, and maintains responsiveness, flexibility. So there are a couple of criteria to that. The 4 pillars of ML pipeline architecture. Efficiency, because it's all about speed. Scalability, because as your data increases, your pipeline should be able to handle that increased data. And you should be able to create templates of your notebook, of your pipeline, so that this can be reproduced. Your pipeline should go in the source control, so that you're not locally modifying Jupyter notebooks, but that is extracted out, put in a source control, just like Jenkins pipeline is a source control, the YAML files are in source control. So your ML ops pipeline should also be in source control, and that becomes your standardization. So like pillars of a traditional CI/CD pipeline, similarly the pillars for the ML pipeline also exist. Now, common ML pipeline architecture steps. So I'm giving out various tools in data ingestion, in data pre-processing, data engineering. How do you train the model? How do you evaluate the model? How do you deploy the model? And in observability, I have given out certain common tools which exist out there, right? These are coming from my experience. Now, how machine learning and LLMs can benefit SRE. This is a topic which is very, very interesting now. So obviously predictive maintenance, because you can analyze historical data and start identifying patterns, and SREs can proactively address these patterns and reduce the downtime. Automated incident response, because when you know that a certain incident has occurred, this has occurred in the past, here is how I had resolved it, I have a runbook for it, let me run that automatically. Real-time insights into system performance. Automatically SRE detects issue faster and respond more effectively. Then content generation is another big one, where automatically LLMs can scan what kind of issues, what kind of resolutions that you've done, so they can automatically create that knowledge management system, and it reduces the stress for manually documenting things, which nobody is good at. We have to admit that. And when you have content generation and it starts maturing, you can then start creating knowledge graphs, where you can analyze large amount of data and identify relationship between entities. So if this issue occurred, then this one occurred, and then it led to occurring this one. So these 3 are related. If this one is occurring today, let me check the other 2 as well. And then finally, from predictive maintenance to predictive analytics, where we can use these knowledge graphs to predict upcoming issues. So that's how an SRE in the future will be able to use machine learning and LLMs. So SRE in the cloud native world, what does it enable you to do? It enables you to balance between velocity and reliability. How? By setting SLIs, SLOs, and tracking your errors easily. Because cloud also offers certain metrics and dashboards, so you can take those informed decisions much easier. Reduce toil through built-in integrations, because you get a one view integrated with minimal setup, which is across metrics, your uptime monitoring, dashboards, alerts, all of that stuff. Right? And then becoming proactive about observability using open APIs. So we spoke in the last topic about open telemetry. So open telemetry already integrates with all the leading cloud providers, so you can collect and export data into your cloud native applications. Now, how SREs can leverage cloud native tech. So as SRE architectures evolve, SRE can leverage cloud native approaches for pipeline reliability and efficiency. So using containers as deployment units, because then you can control deployment units at a smaller scale. You can scale them up, scale them down, you can monitor them, you can put observability tools on individual container rather than putting a big monolith. Observability, we've spoken a lot about this. Elastic scalability, the more modular your application is, the more you can scale certain areas in that instead of scaling the entire application. And then declarative runtime descriptions, we spoke about this, where you can use APIs and you can use the Terraforms, the CloudFormation, the Ansibles of the world to set up these architectures and have all of them within source code. Then there's a sidecar pattern transparency. So what does that mean? So you provide a separate container or a process that runs alongside the primary container application, the application container. So this sidecar handles things like the logging, the monitoring, the security. What does that do? That frees up your application resources, and then you can attach these sidecars, create a template of these sidecars, and keep attaching them to your applications. These can be handled separately. Now, SRE's involvement in system architecture. So obviously the SRE's focus is on system reliability. We all know that. Now, system reliability mandates a reliable architecture, because if your architecture is not reliable, how will you run it reliably? Which means sometimes the architecture needs to be changed to make it more reliable, and any architectural change is expensive, both in terms of money, in terms of time, in terms of opportunity cost. So which means as minimal a change to architecture from a reliability standpoint, the better it is. Which means you have to look at those criteria when you're architecting the application. So architectural change could have been avoided had the SLOs been clear at the beginning. Had you known that this is my service level objective for this service, these are the amount of thresholds that I need to maintain. The system has to respond in 1 millisecond. The system cannot grow beyond these many megabytes, these many gigabytes of memory. I have to stay within that. You could have probably architected the application differently. And SLOs give you clear, understandable, measurable, reachable within the context of the service. So how much horsepower does the service need? What are the expected throughputs, inputs, outputs? If those things are clear, you would probably architect your application a little differently. And that's what the SREs can help you with. And then observability patterns, depending on logs that the system is putting out, the metrics that you're doing, and the tracing. Tracing means tracking one logical workflow and seeing how much that end-to-end workflow takes. For example, in your non-production environment, you are measuring how much does a cart checkout take. So my items are in the cart, I'm doing a checkout. From initiating checkout to actually completing the checkout, that's the tracing. So how much time, how much effort, how many clicks does it take? Things like that. Now, best practices for implementing continuous testing in SRE. So integration and performance testing, a lot of time this is shipped right towards the end before a release. So it's ensuring your components of the system work together, using things like JMeter, Gatling, Locust, whatever you're using. Incorporating security testing, things like your burp suits, your OWASPs, your Nexus, all of that. Establishing observability, where you're using data to identify patterns, detect anomalies, things like that. Even going to the extent of chaos engineering, where you're injecting failures into the system knowingly with a controlled blast radius, and then you are watching the system's response and identifying potential failure spots. So things like Chaos Monkey, Gremlin, Litmus Chaos, there are a lot of tools out there. and then collaborating with the dev teams, aligning on testing strategies, how will I test it, working with the test QA automation team, and working together to address these issues, even taking back to your developers. Now let's look at 2024 and beyond. What are the focus areas and trends for SRE? So CNCF says that the adoption of cloud native technologies has grown. About 78% of the companies using containers in production environment. And Markets and Market report says cloud native application market size is expected to reach 21.1 billion by 2024, growing at a CAGR, compounded annual growth rate, of 22.7%. So you can see there's a lot of focus on the cloud. There's a lot of focus on cloud native technologies, and that makes the role of SREs even more important. So 3 themes around which SRE trends will evolve. Automation. Again, Atlassian states 61% of the IT professionals say as automation will be high or extremely high priority for their org in the next 12 months. Automate anything that's manual, repeatable. Observability. Now with machine learning, LLMs all coming forth, observability will reach a whole new level, because we are going from predictive maintenance to predictive fixing. And then with all of this stuff, the more the data, the more the volume of data, the more the number of people who are involved, comes security risk. So these are 3 things that future SREs have to focus on. Now let's look at a slightly different perspective. SRE people are built different. What do I mean by that? SRE people are built different by design, because they have a solid ability to program and a solid ability to handle operational issues. These are the 2 tenets of a good SRE. They have a unique, uncommon skill set combination. They typically start off as a developer or as a network person, an IT admin, a network ops, an IT ops person, and they slowly gain other skills, slowly go into operating systems, to networking, into infrastructure. And that is why typically there are very few junior people in this role, because these skills are acquired over a couple of years. And that's what gets you to sympathy versus empathy. Where sympathy is, hey, I see you're doing this manually, let me write a script for you. And empathy is, I understand why this must be difficult for you, let's find a solution for you. That's empathy. And that is a very essential skill for SRE. And here's what I believe in: understanding, compassion, trust. Understanding somebody else's point of view, compassion that, hey, I feel your pain, and trust that whatever you are seeing is correct, and that's what you're feeling and that's what you're going through. These are the main tools that an SRE engineer uses. Rest is just software. And I'm going to leave you with that thought. Thank you very much.